Okay, so hello all and welcome to the first of two press conferences at the 54th annual DPS meeting. There's the Division for Planetary Sciences of the American Astronomical Society. I'm Dr. Teddy Kareta and I'm the DPS press officer. And I'm joined today by two representatives of the AAS's press office, Dr. Susanna Kohler and Dr. Kerry Hensley, who I'm very thankful for helping out with today. Let's see. Today we have three speakers presenting a summary of their work that they're presenting this week at the DPS meeting. Before we get started, I'd like to lay out some ground rules and expectations, both about the questions that can get asked and also how you should ask them. First and foremost, today's speakers have taken time out of their busy week at this conference to present some of their exciting work to you, and this has taken a real significant amount of time and effort to prepare on their parts, and I'm very thankful for it. If you could please treat all the speakers and their topics with respect regardless, so their career stage, gender, appearance, national origin, or any other attributes, that would be great. They're doing this for you, and frankly, they're all excited to tell you about their work, and you should be excited to hear about theirs. Second, each of the topics today is of equal importance to the DPS. We'd like this to be reflected in an approximately equal amount of time discussing each of today's speakers' talks, though we know that this is sometimes challenging. After all of the talks is when we're going to actually have the speakers answer their questions, but each speaker will have approximately 10 minutes for their talk, and you can write your questions in the Q&A feature on Zoom, and they will be answered orally afterwards for the benefit of people who are not just on the Zoom call but are watching the stream elsewhere. If you have any questions about the speakers' talks or are looking to get in contact with them, perhaps beyond the contact information they might have provided in their talk, please reach out to me, and I'm going to put my email in the Zoom chat, but it is tkareta@lowell.edu, first initial last name at lowell.edu, I think I said it to hosts and panelists. Let me send it to everyone. I should know how to use Zoom by now. But please reach out to me. I can definitely get you in contact with whoever you'd like and facilitate the kinds of interactions and learning that hopefully you're most curious about. Let me see if I had any other notes to mention briefly. Do any of you have press conference or press things you are distributing after the talk, like releases? Okay, well, you are. Okay. Adam Battle does have one press conference or press release that will be distributed. I'll mention that again when he talks. But without further ado, I'd like to say, thanks each and every one of you for attending today and helping the public understand the exciting and important work that the members of the DPS do. Now, let's get on to our first talk, which is Olga Harrington-Pinto. You can share your screen, and I will read your title slide, and then I will mute myself, turn off my speaker, and you can do your thing. Olga's talk is Carbon Monoxide, Carbon Dioxide, and Water in Comets and Centaurs. Olga is a graduate student at the University of Central Florida. And with that, I will mute myself. Olga, take it away.
Thank you, Teddy. So as Teddy mentioned, I'm Olga Harrington-Pinto, and I'll be talking about a survey of CO, CO2, and H2O in Comets and Centaurs, a paper that is currently in press with PSJ. My collaborators were Mario Womack, Jan Fernandez, and James Bauer. So before I get started with the nitty-gritty of the paper, I'm just going to give a little bit of a background on what we're looking at. So when we're looking at the gas production rates of CO, CO2, and H2O in comets, we're looking at the coma rather than including the tail or any extended sources that are too far out. And the objects that we're looking at are Jupiter family comets, Oort cloud comets, Centaurs, and Halley-type comets. And one of the problems that we faced when looking at these three molecules was the most difficult of the three to observe is CO2. And CO2 is so difficult to observe because there isn't really a lot of there isn't any Earth-bound telescopes that can look at CO2 for comets because of our atmosphere and also because of the lack of its permanent dipole moment. But if you get a little bit further out in space, you can start observing the CO2 in comets. And there aren't that many telescopes that are currently available to look at CO2 in comets. Right now we have JWST, which is amazing, but we have to work with what we have. So working with stuff like NEOWISE and Spitzer, we can untangle the CO2 that we have from there using CO measurements from Earth. Now, in the paper, looking at the CO and CO2 abundance ratios, we used a bunch of techniques, including mass spec, optical region, radio, IR, and UV. And so I'll get started with the graphs now. In the first graph, we're looking at the abundance ratios of CO to CO2. And for all of the graphs, you'll see that the red comets are the ones that are Oort cloud comets. The green one here is a Centaur, and it's 29P. And the purple ones are Halley type comets. This one here is just Comet Halley. And the blue ones are JFCs. So the first interesting thing to note is that beyond 3.5 AU, all of the comets are CO dominant. And so what we mean when we say CO dominant is that it has a higher amount of CO production rate compared to CO2. And when we say CO2 dominant, it has a higher amount of CO2 production rate relative to the CO production rate. Now, if we go below 3.5 AU, we'll see that's where all of the JFCs are located. And those JFCs tend to be CO2 dominated. And if we look at the Oort cloud comets that are below 3.5 AU, we see that they're kind of spread out all over the place. But if we just zoom in a little bit closer to this region where we have the Oort cloud comets that are CO2 dominant, we see that, voila, they all happen to be dynamically new comets. And when I'm talking about the dynamical age, I'm talking about like the inverse of their semi-major axis. And I put their semi-major axis on the top just in case. So they're really, really far out. And if we look at their aging, we see that the dynamically older that they get, they are CO dominated for the most part. And all of these observations here are observed below 3.5 AU. So we should expect them to have enough solar heating in them. So it wouldn't be too much of a problem of like one of them was observed too far out that we would assume that it would be another process that might be affecting them. Now, moving on to a different type of abundance ratio, we look at the CO and CO2 combined versus water production rate. And looking in particular at the comets below 2.5 AU, we use 2.5 AU as kind of a cutoff because that's where water ice sublimation becomes most efficient. And we see that below there, it's about 18%. And based on current literature, we see that that means that it's retained a lot of its natal abundances, which is really cool to find out, like, yeah, comets keep the stuff from early on when they were formed. And finally, we look at the C to O, which is the carbon to oxygen production, or the carbon to oxygen abundance ratio, where we look at the carbon-bearing molecules versus the oxygen-bearing molecules. And again, we try to look at the ones below 2.5 AU. And when we're looking there, we see that the average and the median of those comets both align with CO, or comets forming beyond or below the CO snow line. And so I've put my conclusions, or like the key points of the paper that I've talked about today on this conclusion slide. But yes, there's a lot more to see. This is a very abridged version of the paper. And if you're interested in looking at it, I've put the link in the lower left-hand corner. Thank you.
Okay, and my mask got stuck on my glasses again. You'd think I would know how to do this by now. Thanks very much to Olga for an incredible talk. Next up, I believe, is Adam Battle. I thought Marc was going first. Yeah, so Adam Battle is up next. Adam is a graduate student at the University of Arizona's Lunar and Planetary Laboratory. And the title of Adam's talk, oh no, it is Marc next. I was totally wrong. Oh, yeah, it's a professional thing. I can let Adam go first if you're okay with that. I'm not. All right, consider my apologies to Marc in this respect. Marc is Marc is, can you turn off your microphone briefly just so I can finish introducing you? Thanks. Okay, so Marc is at the Southwest Research Institute in Boulder, Colorado, and the title of Marc's talk is Shape and Duplicity of Lucy Mission Target Polymele from Occultation Observations. And I understand that Marc will be talking about the occultation campaign with some general comments as well. So Marc, it's now, the floor is yours.
Okay, reconfigure the universe here. Actually, the scope of what I'm talking about here is a little bit broader than that original title. we have been very busy getting ready for the Lucy mission for years, and think of what I'm talking about here today as a report from the reconnaissance team, sort of like the Lewis and Clark exploring the North American continent to tell people what's on the western side of North America. I'm trying to figure out as much as I can about the Lucy targets. And we do this with stellar occultations, which is basically a time when one of the Lucy targets passes in front of a star. We look at it with a telescope, the star disappears, and we can use that to measure where it is at the particular time and also get the shape and size of the target. We have 5 targets for the Lucy mission: Euripides, Polymele, Orus, Lucas, and Patroclus. You may not know these now, but by the time the mission's over, they'll be a household word for everybody. In order of encounter, Euripides will be the first one, and we see that in 2027. And we've discovered it's a moon that we found with the Hubble Space Telescope. We did not know that at the time that the Lucy mission was funded, so we get an extra target to look at when we fly by. Polymele, which is, I think, going to turn out to be the most interesting target of the entire mission. We will see that one just a month after the Euripides encounter. Then the next event that comes up is we'll fly by Orus, and that's one of the larger of the objects. And Lucas is a very bizarro shaped body. That one could be duking it out with Polymele for the award for the strangest object we're going to see. And then finally, we're going to end the mission with the prime mission with Patroclus, which is actually a double system, which has a moon that's almost exactly the same size as the primary. And we'll do that in 2033. So this is a region of the solar system that we don't know a lot about, and we didn't at the start of the project. We just had rough guidelines on what the objects, what their rough sizes and compositions are. I'm trying to learn more and to build that into the mission plan so that we can build a more intelligent set of observations and take advantage of our proximity to the objects when we fly by, and not waste all our time trying to figure out the simple stuff. So I'm after accurate sizes and shapes, measuring positions to help with spacecraft navigation, and searching for other things such as rings, dust, or satellites. The occultations to date, we've started this project back in 2018, and this is just a quick listing of all of the events that we've done. I don't know about you, but it makes me really tired looking at this slide, just to think about how much work we've put into this. And I will detail some of what we're talking about here, but you can see that we're doing quite a few events. And 2022 is the craziest year ever for me for doing occultations. We've got 13 international expeditions within a 12-month span. Usually I only have to do one of these international events every year or two. And this is really stretching us. We have been all over the world. Here's a list of the countries that we've been to already for these observations. And we've got some new stuff coming up, like potentially going to the Middle East for one of these. We have maps and details for all of these occultations are listed at the URL you see here. You can get an interactive map and you can see where the shadow falls. We tallied it up, and we have involved more than 500 observers now sent in doing all of these campaigns. This is what I call sort of the ultimate citizen science project. And about 2/3 of these have only done one of these events. We do have a few that repeat. Now, that's not a bad thing. It's not that people do this and say, I'm never doing this again, but it's a consequence of us moving all around the world and involving people all around the world. Here's a quick example. We'd spent 6 weeks in Australia chasing these occultations, and we basically drove all over Western Australia. And I'm not sure how many tens of thousands of kilometers we covered driving around the outback in Australia, but we got some great data. Here's a nice picture showing the skies in Australia with one of our telescopes set up. And there's the galaxy, and then there's the moon is on the left there. So here's some examples of the kind of things that we see. These orange dots show us when the star disappears and then reappears. And then from different telescopes, you get a different set of points. And once you get enough of these, you can figure out the shape of the object. And here you see a largely elliptical shape, but those orange dots do not always fall exactly on the ellipse. You see down here, this bottom part of Patroclus, these points are kind of shifted. That means there's some topography on Patroclus in this part of the body that we're getting a hint from. In Menoetius, there's something strange going up on the northern end. So here's another one of our best examples. This is a different view, and you can see there's some kind of strange mountain thing going on up here in the upper left for Patroclus. And there's some strange things here in Menoetius. So we're building up a 3D view of this object. Here's Orus, probably one of the more simple objects of the 5 targets. But even Orus has there's a departure from this elliptical profile that shows it's got large scale topography as well. In fact, that's kind of the general result of this, is that every one of the targets has topography on it. Could be craters, could be other geological structures. We're going to see a lot when we get there. So here's an example, one of the best data sets from Euripides. This was taken 4 days after launch. I got to watch launch, and then I got on an airplane and flew to Las Vegas, where we had a bunch of people with the telescopes, and we went out and got these data. And you'll see that even Euripides has got something strange going on here. Everything's not just lying right on exactly on the ellipse. Lucas, this is the weird one. And if you just take the metric of how well it fits in the ellipse for being strange or not strange, Lucas is just a bizarre shape. And I can't wait to get there and take a look at this one up close and see what we're going to learn about this one. And Polymele, and I put a picture of Arrokoth on the right. And that's the object that New Horizons went and encountered. The lower lobe of Arrokoth is a dead ringer for the shape and size of Polymele. And you can see that this doesn't fit an ellipse very well either. But we've worked out the geometry from a couple of different events, and it's actually kind of a hamburger shape, very oblate object. And on this particular campaign, we got a nice surprise that 2 of our observers saw a secondary blip that turns out to be a moon that we discovered. And this is not too dissimilar in size from the large lobe around Arrokoth. So it kind of makes me wonder if Polymele is a case of something like Arrokoth, where the 2 bodies never merged. My favorite saying is, that sounds pretty interesting. Let's send a spacecraft there and have a look. Should be pretty fun. And this is a scale drawing. If we make a lot of guesses about what the orbit might be, and this is kind of our best shot. You can see Polymele here in the middle, and then Sean off to the side. And now the challenge is on to see if we can find this again. We cannot do these observations without our observers. Here's the crews that we had in Australia, and here's the crew we had in Asturias, Spain in October last year. Here's a group in Senegal observing Orus just last year. And here's the group in Las Vegas trying to get Euripides. This is just but a few pictures of the teams. And you can imagine, once we get the picture gallery up for all of them, it's going to be quite an impressive list. And we've had we invited everybody that's been involved to come out and see the launch. So here are the people that from around the United States that came and flew in to see the launch. There's Lucy is sitting on the launch pad in the background there. You can see the logo up on top. And less than 24 hours later, we got to see this and get to see it go on our way. So we're all set and ready for all these encounters. And Lucy's going to have a flyby of the Earth here in just a couple of weeks as it continues its journey out to the Jupiter Trojans. Thank you very much for listening.
Okay. You might need to turn up your audio, but I will just keep talking. Okay, so from the composition of outer solar system objects to the shape and structure and cratering, perhaps, on the Jupiter Trojans, let's move on to our final talk of the day by Adam Battle, the University of Arizona, who I already introduced mistakenly earlier. Adam Battle will be talking about evidence for shock darkening / impact melt on a near-Earth asteroid to close out our cratering theme of the second half of this session. So with that, take it away, Adam. I will mute myself.
Awesome. Thank you, Teddy. I'm really excited to be here, and I will slides and get started. So as Teddy mentioned, I will be talking about evidence for shock darkening or impact melt on near-Earth asteroid 1998 OR2, and I'll largely just be calling this OR2 for most of the talk. I have my name and institution listed here, but I also want to give a lot of thanks to my co-authors and collaborators who've been really helpful, especially my PhD advisor, Professor Vishnu Reddy. And there's a little video in the middle that shows our photometry tracking. So this is a star field with the asteroid OR2 moving through the middle, and this is a video of images we took to get the photometry to confirm the rotation period. So it's kind of fun. But OR2 is a near-Earth asteroid that is listed as potentially hazardous due to its size and how close of an orbit it makes to the Earth. I have here on the left kind of a solar system dynamics plot of a bunch of orbits. You can see the sun in the middle, which is circled by Mercury, Venus, Earth, and Mars. And here is OR2, this kind of white oval, and it makes a really close approach to Earth sometimes, and it did one of these close approaches in April 2020. But this is where the asteroid was kind of at the start of DPS this week. So the asteroid is about 2.2 kilometers wide, or about 1.5 miles. And even though it's called a potentially hazardous asteroid, there's really no threat to Earth. We know its orbit very well, and we know when it will make close approaches, and there's no threat necessarily. It's just one to keep an eye on and good to characterize. And I mentioned that video where we monitored how bright the object was, and we were able to confirm that it had a rotation period of about 4.1 hours. But really what happened was in April of 2020, it was making one of these close approaches to the Earth at about 16 times the distance between Earth and the Moon, so 16 lunar distances. And our goals were to observe it, constrain the rotation period, as well as the composition for OR2. The observations that we took, we did visible spectral observations, which were done with Raptors 1 on the campus of the University of Arizona in Tucson. And so here I show a picture of that that's located on the roof of the Planetary Science Building. We also used archived data from the MITHNEOS survey, which is near-infrared data taken with the IRTF. And so I show a photo of that on the bottom, and I give credit to Ernie there for the beautiful picture. And then we also used the photometry from the Leo 20 observations, Leo 20 telescope, which is also located in Tucson, as well as additional information from Arecibo and NEOWISE that is really important for having kind of context for this asteroid. So here I show some of the initial results, and I'll walk you through some of them in a minute. But this is the spectrum of OR2 compared with some different taxonomies that we want to look at. So here we see a plot of normalized reflectance on the y-axis, so how much sunlight it's reflecting to the observers. And on the x-axis is the wavelength in microns. So this is what makes our spectrum. OR2 is the black and blue spectrum, kind of in the middle here. And the black line were the visible observations that I collected, and the blue line are the archived near-infrared observations that we were able to use. And they combine to make this full spectrum with lots of information. But they're compared here with, on the left, the S and Q type asteroids, which are known to be linked to ordinary chondrites. And you can see they have very similar shapes. So there's a peak at around 0.7, there's a dip around 0.9, another dip around 2 microns in wavelength space. So they have overall very similar shapes, but the scale is way off. So they don't kind of have the same range of absorption and reflectance. On the right are the two closest matches that an online taxonomy tool told us, the SMAS online taxonomy tool. So these are what the computer is showing as the closest match. And these are both kind of dark asteroids, and the closest match itself was actually the CH type in this blue line. So the computer's telling us, this is a carbonaceous asteroid. So there's a bit of kind of confusion there, because with the plots on the left, we're actually able to measure band parameters that tell us the mineralogy we see on the surface, and it does indeed match ordinary chondrites. So we're seeing characterization showing us mineralogy that matches ordinary chondrites, but the taxonomy is telling us it's a carbonaceous asteroid, and those are very different. So we wanted to investigate what that difference is. So we looked at a bunch of different factors, including space weathering, grain size, metal content, and different viewing geometries for the asteroid. And we were largely able to rule all of these out, with only shock darkening and impact melt remaining as a strong candidate for what could be altering our spectrum of OR2 from an S-type, sort of that ordinary chondrite that I showed on the left in that plot, to what we see in our telescope observations. I'll get into what shock darkening is on the next slide, shock darkening. But here I just show a plot, or an image of the meteorite Chagach, which is a shock darkened H chondrite that we used in a meteorite study to look at the effects of the shock darkening in that ordinary chondrite, and kind of confirm that this is a potential effect that we're seeing in our spectrum, so that it helps support OR2 being dominated by shock darkened material. So shock darkening occurs when something impacts a planetary body and the temperatures and pressures are high enough that some of the rock on that surface is melted. And impacts are pretty common in the solar system, but this melting of the rock alters the body's appearance, both to what we see with our eyes. So here I show an image of the Chelyabinsk meteorite, and you can see these dark, this kind of dark veins and matrix that these white rocks are sitting in. So you can see those shock darkened material there. But it also affects the spectra of the object that we take. And the difference between shock darkening and impact melt, and the reason it's, shock darkening, impact melt, or SDIM throughout all my slides, is that it's largely just the degree of melting that occurs. So it's the same type of process occurring, just the temperatures and pressures scale higher, you get impact melt, and if they're scaled a little less, you get shock darkening. But kind of the big important thing is that the composition is unaffected. And so what we're seeing in that slide with the spectra is that OR2 is being altered, and kind of the scale is being changed, even though the composition is being unaffected. So this is the shock darkening causing an incorrect classification, which leads to misunderstanding of the asteroid's properties. And so impacts are really common in the solar system. I threw some pictures here of different objects that have lots of craters. So there's from the NASA Dawn mission, images of Ceres, from the Rosetta mission, images of Steins, from NASA's NEAR mission, image of Eris, and these all have lots of craters. So they're really common in the solar system, but seeing shock darkening and impact melt is exceedingly rare. It's not common at all. So in the asteroid population, we've seen it in 1 or 2 cases in the main belt, but that's about it. And in our meteorites, we see only about 2% of ordinary chondrites have stages of shock darkening and impact melt on them. So it's a pretty rare process. And so it's really exciting that we're seeing, we're increasing from 1 or 2 cases to now maybe a 2nd or 3rd case. We're seeing this in a near Earth asteroid, so something that's closer to our planet. And this is important because it is changing the taxonomy that we return from that online tool. And that taxonomy relates to physical properties of the asteroid. And I give an example here. So C-type asteroids are usually largely are lower density, and the rocks on those meteorites are more fragile. S-types are usually higher density, and the rocks are more cohesive and strong. So getting that taxonomy confused can also change how you interpret the physical properties of the asteroid. So I have here my summary slide that says we have visible and near-infrared spectroscopy of OR2, and the spectra match ordinary chondrites because we can measure the mineralogy, but the computer returns a carbonaceous taxonomy. And shock darkening is the most likely cause of this alteration. And we have some meteorite analog analysis to support this that we did in the lab. And this is the first evidence of shock darkening dominating the surface of a near-Earth asteroid. This is the first time this is being seen. Some of the takeaways for kind of the bigger picture are that shock darkening caused us to incorrectly classify asteroids, and that this kind of ordinary chondrite material, like we see with OR2, could be hiding on asteroids classified as the C or X type. And this affects our understanding of asteroid physics. And so my last thing here is a play Doppler image of OR2 that was taken with the Arecibo image. It's a really beautiful, video. And I have here my contact information at the top, as well as a link to the paper, which is available on Planetary Science Journal.
Okay, well, I'd like to thank each of our speakers, very especially Adam, Dr. Marc, who I think I forgot your doctor the first time, but Dr. Marc, and Olga. I am going to let them use my laptop to have a consistent source of audio so we don't have to deal with the muting and unmuting. But I'd like to just thank each of them again for finding the time today to present their talks before we go into the Q&A. And I'd also like to thank Doctors Kohler and Hensley as well. So I'm going to move my laptop over there, and then you two, you're on track to do the Q&A stuff.
And it looks like we don't have any questions in yet, but if anybody in our audience has questions, please go ahead and submit them via the Q&A box at the bottom of your Zoom screen.
Does everybody have access to the chat window within the Zoom?
The attendees do not have access to the chat window. There is a separate Q&A box for submitting questions. That's to make sure that we answer questions out loud.
Okay.
I wanted to ask Marc, how do you go about recruiting your observers for the occultations?
Okay, so there's a long answer and a short answer. I'll do something halfway in between the two. I realized as I was putting this stuff together, I've been doing occultations for 40 years now. My first one was as a grad student at the Lunar and Planetary Lab with a 61-inch telescope and wrote a whole data system and used a CCD for the first time ever. Okay, so I'm not going to recount 40 years of history, but I've been in the game for a long time. And I've been all over the world doing occultations. And everybody that I run into and involved in all these projects, I never forget who's interested in occultations. And they all have friends. And I say, hey, you got a friend that wants to do an occultation? So it's just an intense networking process where that I build up this cadre of people that I train and teach them how I like to do science and involve them all the way through writing the paper if they wish to be involved at that level. And I've got a Slack site that I've now kind of worked on incorporating. I think we've got 1,000 people that are members of that site. So whenever a campaign comes out, I put the call out to there and say, hey, there's an event. Are you interested? And it's just still growing. And it's at this point, it's kind of like word of mouth, and it's kind of snowballing. It's really great. You would not believe the aspect of community that we build up for each one of these campaigns. It's very addictive for everybody involved.
That's very cool. Is there a way for somebody who might be viewing this video later to get involved? You have a website or something?
You know, it's rare to take somebody cold off the street. You know, it kind of comes by a referral process. So if you know somebody that's into it, but there's also, if you search for International Occultation Timing Association, or IOTA, and there's a North American chapter. If you search for that, there's a lot of contacts and people. And if you're interested in doing occultations, you should start there and work with the amateurs and kind of ease into the game a little bit. And with enough practice, and it doesn't really take that much. It's you kind of get known, and then so you can kind of get a referral process. And so if somebody contacts me and I've never heard about them, it's hard to know just how to integrate them into a project. But there are many, many pathways. It's not like, I'm not looking for a flood of email from people that I've never heard of to just come and say, join it. Because gets very technical. It's usually a 4-day pattern in the field where we spend the first night teaching everybody how to use the gear, second night practicing, third night dress rehearsal, fourth night event. By the time you're done, you can go from nothing to being an accomplished occultationist in 4 days. But yeah.
That's great. Yeah, thanks. So it looks like we do have a question in from Richard Lovett, freelance. This is a question regarding the shapes of the Lucy Trojans. What can these tell us, even before Lucy gets there, relevant to our understanding of asteroid formation and other solar system history?
There's two things that we can pull out of this right away. It takes a little bit more work. So anytime you find a moon around an object, you then get to measure the mass of that system. So out of the 5 targets, 3 of them are multiple systems. So we have masses already for all 3, and we get sizes. That means we have densities. Now, in the case of Polymele, we don't have an orbit yet, so we can only guess at the density. But this is the thing that we're after. It's a tracer of the internal composition. If we found a Trojan out there with a density of 5, kind of like the Earth, you're going to really scratch your head and say, where the heck did that come from? But we can compare them to the main belt. We can compare them with the Kuiper belt and put it in the context of where did these things come from. The second thing, which is a little bit of a surprise to me, is if you think about the history of the space program, one of the things that happens when you send a spacecraft by is that what do you see on just about every planetary solid surface? It's craters, right? And there's a lot of people that work on studying those craters because it tells you about the impact history. It tells you about the history of the solar system and the evolution of sizes and bodies and how you tie all this stuff together. It's a very long, complicated process, but it all starts with the craters. What I'm finding is that if you get the right kind of occultation data, I think we can start characterizing the cratering record on an object without sending a spacecraft there. Now, you need to have a couple of good test cases for that, and Lucy's going to be perfect because we've got all this great data using to help Lucy get there. Lucy's going to go and take all this data that we can compare in detail back to the occultations and use it as a training set. And then I can go off and survey thousands of asteroids, whatever your favorite asteroid is, whether it's a near-Earth asteroid or all the way out to the Kuiper belt. Independent of the distance, I can tell you this object has never been hit, or this thing has been beat up like crazy. And that to me is one of the most exciting things that's come out of this prep work that we've been doing.
Susanna, if there aren't questions for the other two, I definitely have questions for Olga and Adam if there is time.
By all means, go for it.
Okay, well, I'll start with Olga. Olga, you were talking in your very interesting talk about how these dynamically new comets seem to have more CO2 than CO, which is definitely different from, I think, what a lot of people might have expected. Right? Yeah. I was wondering if you could talk about that a little bit more. And if I remember correctly, you also mentioned that you had some predictions for C2017 K2, one of the brightest comets in the sky right now, which might be a good, like backyard telescope target coming up for the winter.
So, well, first of all, for everybody online and for Teddy, everybody might think that CO comes off because it has an easier temperature to reach. So everybody would expect the CO to be depleted. But to find that there's so much CO2 in there, it's just kind of like, compared to the CO, it's just kind of mind-boggling. And we think galactic cosmic rays are the ones that are affecting like the outer shell. So the CO is kind of depleted on the outside. So when it's coming in, we see more CO2 than CO. But yeah, when we're looking at K2, which is a dynamically new comet, we can kind of test this out. We can see how it's going to compare with its relative abundance ratios, and it should be in that CO2 dominated region, or maybe like really low in the equal parts region, that it would be there. So people have time, please check it out.
So when people are observing K2 with binoculars, maybe come December, you know, we can think about, you know, all the interesting work that they're doing here at the
Of
DPS.
course, I mean, I think it's a good citizen science movement, and like they can get visual light curves of it. And I mean, K2 is an amazing object as it is, so it'd be just cool to have more data from it.
Sure. Thanks.
Thanks.
Susanna, can I keep going?
Yeah, go ahead.
Okay, Adam, so for your work, I think it's really exciting that some of these asteroids you're finding that might look carbonaceous are actually kind of hiding this stony composition. Are there any kind of next steps to your research, likely next targets you want to look at? Or is this just the kind of the first step in what might be a longer process of understanding what's going on?
Okay, yeah, thanks, Teddy. So definitely there were some unique things about OR2's spectrum that made it easier than other objects to rule out other effects like space weathering, grain size, viewing geometries. So it was definitely one of the easier cases to identify shock darkening and impact melt. I think now that we've kind of gone through that first process, it'll be a little bit easier now to look at other cases that might have a mixture of those. And so we do have about 4 candidates that we're starting to look at that are also candidates for having shock darkening, but mixed in with a few other alteration processes. So you kind of have to be able to sift through the combination of effects. So that would be the next step, as well as you know, more meteorite analyses in the lab will also help us understand what's going on in the rocks in space. But definitely, I think shock darkening is worth, you know, getting some more attention going forward.
Sure, and it must be exciting for you to be working on, you know, a topic related to impacts, you know, only a week after the DART impact, I assume.
Yeah, it is really exciting. You know, seeing that we've seen this effect that can alter how we understand the physical properties of the asteroid, and then seeing, you know, a kinetic impactor in the DART mission. They tie really well together, because if we see an asteroid and misunderstand its physical properties, like its density or its mass, that changes how we understand the impactor process. So it is a really exciting kind of comparison.
Cool, thanks. All right, Susanna, are there any more questions online?
Yeah, we got a follow-up from Rick Lovett for Marc. How often do you get usable occultations, as in bright enough stars, for any given asteroid in this size range?
The answer to that is it depends on the size of telescope that you have. We've got an event in 3 weeks from now that's in Spain and France. That's a 9th magnitude star, which doesn't mean a whole lot to anybody. But I'll tell you this, just about anybody in the world that has occultation gear, even the tiny little camera, can do this event. We have one of those that's that bright. Everything else that we're doing that you saw on the long list at the beginning of my presentation, those all take fairly substantial telescopes, like 11-inch, 16-inch telescopes. And there a normal year would be 2 or 3 events out of the 5 objects. This year is anything but normal. I had to turn events away. I think that the list was I probably could have chased 100 different events all over the world and died in the process. And as it was, I whittled it down to about 13 or 14. So it varies a lot. And one of the things that it varies about, takes 12 years for the Trojan to go around the sun. Every time it makes one transit around the solar system, it passes in front of the galaxy twice, once in the north and then once in the south. When it's crossing the galactic plane, there's a lot of stars there, and the rate of events goes way up. That's what's happening right now. And so between now and 2027, I expect it's going to be a much lower number. Each given object might have 2 or 3 events between now and 2027. So, and maybe I can get my life back.
Great, okay. I do not see any other questions at present.
Okay, I can start to wrap up if you'd like, Susanna.
Sounds good, yep.
Okay, well, first and foremost, thanks very much to each of our three speakers, Olga Harrington-Pinto, Dr. Marc Buie, and Adam Battle, for their excellent presentations today and for finding the time to answer these questions. I know that this will be posted online, so if those of you might be watching later, perhaps it's in the middle of the night where you are right now, and you have any questions for the speakers, they might have provided contact information for you in their talks, and if not, you can certainly reach out to me at tkareta, Kareta, at lowell.edu, and I will definitely put you in contact with any of the speakers about whatever you like. Thanks very much to Dr. Susanna Kohler and Dr. Carrie Hensley for their help in setting all of this up today. I hope that more than anything, this press conference and the one that's coming on Thursday gives you a good idea on all the cool and interesting work that people at the DPS are doing, from meteorites to gas chemistry to hunting for moons and shapes on the Jupiter Trojans. I think we're doing exciting work around here, and thanks very much for tuning in today. Consider this the end of the press conference. Thanks for tuning in.
And I've dropped a link in the chat to the media advisory, which you can find off of the DPS 54 website. And that's where we'll be putting the presentations from the speakers, the video recordings, any press releases related to that.
Great.
Looking forward to seeing you on Thursday.
Yeah, thanks very much, everyone.